Welcome to this explainer. Okay, today we're basically playing chemical detectives. We're going to solve the mystery of where exactly these invisible electrons go during redox reactions. I mean, have you ever looked at a rusting piece of metal or wondered how we actually get pure, shiny copper out of a dusty rock? Well, the secret lies in this microscopic exchange of power, a totally invisible transaction happening right under our noses. By the end of our time together today, you'll be able to track exactly who's stealing electrons and who's giving them away.
Here's our quick roadmap for the investigation. We're covering the basics of redox, tracking electrons with a handy rule called oil rig, checking out the oxidation number rulebook, writing half equations, and finally spotting redox in the lab. Let's get right into it.
So, part one, the basics of redox. Let's just define exactly what we mean when we say a chemical has been oxidized or reduced. This terminology can honestly trip people up, but it is the absolute foundation of our entire investigation here.
Think about this. When a chemical loses an electron, where does it actually go, right? We have to remember a fundamental rule of the universe here. Chemical reactions, they never happen in isolation. If something is lost, well, something else must, without a doubt, gain it. Electrons don't just vanish into thin air. If one atom throws an electron away, another atom's got to catch it.
Now, historically, scientists actually looked at this just as the transfer of oxygen atoms. Like, if zinc oxide reacts with carbon to form zinc and carbon monoxide, the carbon gained oxygen, so boom, it was oxidized. The zinc oxide lost oxygen, so it was reduced. But the modern definition, it's actually about something way smaller and way more fundamental than oxygen. It is entirely about the subatomic level. It's all about the electrons. Moving on to part two, tracking electrons with oil rig. To really grasp these reactions at that molecular level, we need to arm ourselves with the right investigative tools. We're zooming way past oxygen now. And this little mnemonic is your absolute anchor. It's going to save you from so much cognitive overload. Just remember, oil rig to track the movement of electrons. Oxidation is loss. Reduction is gain. Seriously, keep this front and center in your mind, and you'll never get lost looking at a chemical equation again. And this perfectly illustrates the core of redox reactions. Oxidation and reduction literally always happen together at the exact same time. Actually, that's where the word redox comes from anyway. It's just a mashup of reduction and oxidation. So, if we have a magnesium atom and it loses 2 electrons to become a 2+ ion, it's been oxidized. But those electrons gotta go somewhere, right? If hydrogen ions catch them to become neutral hydrogen gas, they've been reduced. One loses, the other gains. A package deal, always. All right, part three, the oxidation number rulebook. So how do we actually keep track of this invisible accounting of lost and gained electrons, especially when reactions start getting, complicated?
Well, we use oxidation numbers. These are basically our clues, little tags assigned to an atom or ion to help you track exactly where the electrons are moving. Think of them like a financial ledger, but for electrons. They tell us the exact degree to which an atom has been oxidized or reduced. And, quick note, unlike regular math, check out the formatting, we write the plus or minus sign before the number, like +3, to denote that charge state.
Memorizing the rules in this playbook lets you deduce the oxidation state of pretty much any element in a reaction. Look at the first rule here. An uncombined element, like, say, pure hydrogen gas or just a solid block of zinc, has an oxidation number of 0. It hasn't lost or gained anything yet. Group 1 elements, always +1. And crucially, if you look at a neutral compound like sodium chloride, the sum of its oxidation numbers is exactly 0. Honestly, once you know these rules, you can crack the code of almost any complex molecule to find out what its electrons are up to.
Which brings us to part four, writing half equations. Let's head straight to the scene of the crime and see how this all builds into tracking an actual displacement reaction step by step.
So we start with a full equation, right? Where a more reactive metal displaces a less reactive one. In this case, solid zinc reacts with aqueous copper sulfate to give zinc sulfate and solid copper. But if we write out all the ions, it just looks like a tangled mess of letters and numbers. There's way too much noise here to see what's actually going on. To clear the air, we need to drop the spectator ions from our inquiry. Take a look at the sulfate ion, SO4 2-. It goes into the reaction as SO4 2- and comes out completely unchanged. Same exact thing. It doesn't exchange a single electron. It's literally just sitting in the bleachers eating popcorn watching the game happen. So we cross it out. Getting rid of these spectators leaves us with a beautifully clean ionic equation. And from that clean ionic equation, we write our half equations. By breaking the reaction down step by step, we totally expose exactly who lost the electrons and who gained them. First up, zinc goes from neutral to a 2+ ion. Because it became positive, it must have lost 2 negative electrons, so we plop a +2e- on the right side. Oxidation is loss. Meanwhile, the copper 2+ ion takes those 2 electrons, putting them on the left side of its equation, to become neutral solid copper. Reduction is gain. And always double-check your work by making sure the charges on both sides of your half equations balance out to 0.
Okay, our final stop, part 5, spotting redox in the lab. It is super great to do atomic bookkeeping on a piece of paper, but how do we prove this is actually happening in physical reality? Like, how do we see the invisible? Well, we use specific chemical tests. For instance, potassium manganate 7 is an incredibly powerful tool here. When we add it to an unknown solution, it visibly confesses that a redox reaction is happening by changing from a deep, vibrant purple to completely colorless. That fading color tells us without a shadow of a doubt that our mystery substance contains a reducing agent. On the flip side, we have potassium iodide. If we suspect we're dealing with an oxidizing agent, we just add potassium iodide. If the agent is there, the clear solution suddenly turns this striking red-brown color. That's our clear-cut visual proof that the iodide has lost electrons and formed iodine. So, the absolute crucial point here is understanding the roles of these chemical agents. And fair warning, this is a very common place to get tripped up, so stick with me. An oxidizing agent causes another substance to be oxidized, and in doing so, it becomes reduced itself. A reducing agent does the exact opposite. It causes another substance to be reduced by giving away its own electrons, literally sacrificing itself and becoming oxidized in the process. It is a beautiful, perfectly balanced exchange. I want you to think about that for a second. Since the entire chemical industry relies on these exact electron transfers to extract vital metals from their ores, what would our modern world even look like without reducing agents? We use them like carbon to rip oxygen away and give electrons to metal ores just to get pure iron for our buildings, our cars, our infrastructure. Without these reducing agents sacrificing their electrons, we'd literally be stuck in the Stone Age. Keep that in mind next time you see a raw, shiny piece of metal, and remember that mastering these invisible electron transfers is the absolute key to unlocking the entire modern chemical industry. Thanks for joining me on this explainer, and keep asking questions.